Booyah! Section 9.3 Taylor series, specifically Taylor and Maclaurin series. Now here we go. We're going to try to get this first pass in under 30 because I told you had to do some homework last night. So let's go ahead and take a look at this. What's the difference between a Taylor and a Maclaurin series? Well, a series, we all know, has that little sigma guy. We call it a power series, and if it's centered at x equals 0 like this one is, we call that a Maclaurin series. Vice versa, if we have a power series that's centered at x equals c, where c is a constant, in the above we got an equal, it's exactly equal to all of this stuff, but since it's not centered at 0 but centered at x equals c, those guys would be called Taylor series, all right? Now this next little paragraph here says exactly what we're trying to do here in this section, okay? The equal sign above means that the left side equals the right side, thus making it an identity. Okay, and the question is, when it's centered at x equals c, for what values of x does the identity hold? We have to find them. For all such values of x values that hold, we say that the series converges. For the values of x where the identity is not true or doesn't hold true, we say the series diverges. Okay, for a particular power series centered at x equals c, exactly one of the following must be true. 1, the series converges only at x equals c. All power series converge at their center. 2, the series converges for all x. Or 3, they converge for specific values of x, or they diverge for specific values of x. We also have something called the radius of convergence for a power series. Okay, and there's 3 things that can happen. In part 1 above, we say the radius is 0. So if it converges only at x equals c, which it always will do, we say the radius is 0. 2, if the series converges for all x, then we say the radius of convergence is infinity, or everything. And 3, part 3, if we get a corresponding domain, then we say that is the interval of convergence, or we call it the domain of the power series. Now, what the heck is all of this stuff talking about? Let's say we have y equals the natural log of x. Okay, and I'm going to use a series to represent this centered at x equals 1. So I could write that stuff all above. It'd be x minus 1 to the first, x minus 1 squared, right? And we all did that when we wrote out the Taylor polynomial. If I put a little series and add those guys all together, well, hey, that's going to give me an exact series for that, okay? And then what we're trying to find is can I go a little bit this way? Can I go a little bit this way? And would it still converge? Would that still hold true? Would that power series hold true? And so what we're going to do is we're going to find, we know it works at 1, right? If it only worked at 1, when we look above, we would say the radius is 0, okay? But can it go and believe it or not, for this one, and we'll show it in a little bit, you can go 1 to the left, you can go 1 to the right. So it would be 0, 2. And as long as you're in between 0 and 2, then we would say the series converge, or the series is good to go, right? It's exact. Anywhere above that, it doesn't do a good job of, it's just too much stuff going on, right? It's not going to give you the exact answer. We can't use that equal sign, right? And we want that equal sign, where it's perfect, where it's exact. And as long as you're between 0 and 2, you're good. Now, the other thing we're going to find out is, since I do have a radius of convergence of 1, because I can go 1 to the left and 1 to the right, we're going to have to check endpoints. And the only way that you're able to check endpoints in this section is we usually want to do 99.9% of the time the ratio test. So I'm not going to do it for this one. We'll do some examples, but believe it or not, natural log, you can't even have 0. So if you did all the math, you would find out that 0 cannot be included there, but it is included there. Now, how the heck do you figure all that stuff out? I'm about to show you. Okay, so let's keep rolling. Okay, right, like I said, we're going to try to keep this a half hour. I need you doing some homework at home. All right, example 1. Okay, sorry, got a quiz dropped off. All right, example 1, based on the fact that a 4th degree Maclaurin polynomial, e to the x, is this, and we all should have known that, right, from our Taylor polynomial series. Okay, find the nth term. Then find the radius and interval convergence for the representative power series. So we all know for this bad boy, I'm going to probably have to show a little bit more work. So let's go ahead and go to my blank screen. Sweet, I got my little Let's get our marker up here. So we got e to the x, and we're going to do this. I think it had for 1, right? So it's 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial plus x to the 4th over 4 factorial. And they wanted me to do a series out of this bad boy. Well, how the heck do I make a series out of this bad boy? Well, that means e to the x is equal to the series. N equals 1 to infinity, right? Ooh, n equals 0, right, to infinity, because my first term would be e to the x, or shoot, I probably should have left that blank. I'll help you out with how we figure that out. And now what I have to try to do is to put an equal sign there, and I'm going to add all these guys together, thus making it a series. I need to know what the nth term is. So I got plus plus. What the heck is the nth term? This is where we have to create some of these, and these can get a little bit difficult. Okay, I went a little bit too quickly right there. All right, but let's say I think this is just going to be x to the n over n factorial, right, class? And then if I go plus then I can make that an equal sign right there. If you remember, for the Taylor polynomial or the Maclaurin polynomial, for both of those in the earlier section, we just stopped. And since we stopped, we needed the squigglies, right? But now I can do equal signs because I have it going to infinity. Okay, so that's good to go. So now what I'm going to do is I'm going to create that equal sign, but then I'm going to turn it into a series, right? Because we're going to look at a lot of these guys in this chapter. And we know we're going to go to infinity. Why? Because I made that an equal sign. And then I just need to know where I start from, right? And for this particular one, I would have to start at n equals, let's see. If I put a 1 in there, that would be x. And it doesn't start at x, right? It starts at 1. If I put a 0 in there, works out beautifully. So I could go n equals 0. And then some of you are going to say, well, could I maybe have done x to the n minus 1 over, n minus 1 factorial and started at n equals 1? You're 100% accurate, okay? But a lot of these we see start at n equals 0. We go to infinity. This would work out also, okay? It's not a right or wrong. But this right here, as long as I go x to the n over n factorial, this means the same exact thing as that. I can have the equal sign because I am going forever and ever. All right, so now what we're going to do, okay, now this is obviously centered at 0, right? That's my polynomial, my Maclaurin polynomial for e to the x. It's going on to infinity. I got that equal sign. But now we're going to do that extra stuff, right? We're going to find out, hey, does this only work at x equals 0? Or is there an interval of convergence that I could work with? Would this work for other values of x? So that's what we're trying to figure out now, okay, you guys? And to figure out that all of this stuff, we are always going to go to the ratio test, okay? So that's why I needed us all so good at 9-1. All right, so let's do the ratio test for this bad boy. Well, how do I do the ratio test for this guy? Well, it is simply the limit as n approaches infinity of the n plus first term, a to the n plus first term, over the a sub n term. Well, I'm going to save a step, right, since we just got done doing all that stuff, and I'm going to already multiply by the reciprocal, okay? And remember, we got absolute values there, and the ratio test tells me if it's less than 1, then that is when I'm going to converge. All right, so let's go ahead and do this work. Pop quiz coming up. Let's go. So we got equals. Equals. Oh, no, it says it's working. Sweeties. Sweeties. All right. I think I got enough room here. We'll see if we do. All right, so now we have equals the limit as n approaches infinity of, I can go x to the n times x all over n plus 1 times n factorial. Remember to show all of your work, you guys. The AP graders need to know you know what you're talking about, okay? Those guys cancel out. Those shling equals the limit as n approaches infinity of x over n plus 1, absolute value. Now, there's something interesting there, right? This is the limit as n approaches infinity. Well, x, believe it or not, even though it's a variable, we're going to treat it as a constant. And so I can go ahead and evaluate that. That's x, a constant, over infinity, which that's going to be 0. And guess what? Since that's going to be 0, that's less than 1. Now, what does that tell us? That tells us that it converges by, sorry, I'm running out of room, the ratio test. Well, guess what? That means who cares what x is? this dude is always going to converge. So then we make some conclusions. All right, and so I'm going to erase this so I can make some conclusions, and I'll get a new piece of paper out there so that I can write all this out. So we're going to say the radius of convergence. So write this down here. The radius of convergence is infinity. Well, if the radius of convergence is infinity, then the interval of convergence is negative infinity to infinity. Booyah, done, right? Regardless of what x equals. So that was a very powerful Maclaurin series. Okay, it's going to give me exact answers. Doesn't matter what x is. That thing's going to work out. It's going to be good to go. Sweetie sweets. Well, Mr. Tanaka, what happens if it isn't good to go? Well, believe it or not, it gets to be a lot of fun because it means I got to show a lot of work. All right, so let's look at some other examples here, okay? We're going to start with 2a. I've got to write it on the other page here, okay, because there's going to be a lot of notes that we've got to take here, okay, class? All right, so here we go. Let's do the series. N equals 1 to infinity. Ooh, this time I'm starting at 1, and we're going to go from negative 1 to the n plus 1 times x minus 5 over n all over n 2 to the n. Now, a lot of us should say, oh, that looks like an AST, but you know what makes it a power series? What makes it a power series is that it not only has n's in there, it has a x. And whenever it has an x in there, then that means it's a power series. And whenever it's a power series, this dude, hopefully you have an idea that that guy is centered around 5. It's a power series centered at 5. How do I know that it's got an x? And the x minus 5 means it's centered at 5. And I need to know for what values of x would this dude converge. All right? We just got done doing series like this with converge, diverge, and you needed to know so much stuff. All right, but what do we have to know in this particular case? Ooh, it looks like I lost my, oh no, I'm still in that screen. All right, here we go. So what do I do in this case? Well, bang, bang, right? I didn't have to make up this guy, thank goodness. I just got to ratio test this bad boy. Well, how do I ratio test this bad boy? Well, it's just the limit as n approaches infinity. Absolute value. Class, what happens to that negative 1 when I take an absolute value? Turns everything positive. So guess what? I can throw that bad boy out of there, and all I got to do is x minus 5 to the n plus 1 all over n plus 1 to 2 to the n plus 1. And I'm going to divide that bad boy by the a sub n term or by the reciprocal, and I get n 2 to the n all over x minus 5 to the n. All right, let's keep doing work. I need to know if that's less than 1. That's at least going to tell me when this converges. Okay. So let's set that equal to the limit as n approaches infinity. All right, let's simplify. That's going to be x minus 5 to the n times x minus 5 all over n plus 1. And show your work, right? 2 to the n times 2. Okay, and then I got an n. I got 2 to the n. I got an x minus 5 to the n, and then I'm going to spling. Everything else is good to go, right? I think so. So here we go, equals the limit as n approaches infinity of x minus 5. Ooh, I'm going to multiply that by n all over 2 to the n plus 1. Well, I said in the last problem that x minus 5, that's just a constant. So if we go n behavior model here, that's an n over an n plus 1, which infinity over infinity, right, is equal to 1. Ichi! So if it's equal to ichi, then that means for this guy, I get x minus 5, over 2. And I need that bad boy right there to be less than 1, because the ratio test tells me if it's less than 1, then it converges. Okay. All right, let's work with this a little bit more then. Well, because that's an absolute value sign. Well, the first step you guys might say is, oh, that 2 is positive, so I can multiply that 2 on both sides. So I get x minus 5 is less than 2. Now, when you have this x minus 5 where it's centered about all by itself, believe it or not, that 2 is called our radius of convergence, is 2. Okay, the radius of convergence is 2. So if you remember that natural log, we went 1 to the left and 1 to the right. For this one, we're going 2 to the left, 2 to the right. And if we remember our inequalities back from our Algebra 1 days, right, I could set up this little bad boy. Okay, right? Isn't that how we get rid of a absolute value? For sure it does. Add 5, I get 3 is less than x is less than 7. And then what the what, right? Remember that stuff? Remember that stuff? It might be equal to, it might not. So right now what it is I have my problem. I have to do my interval of convergence. Remember, we always go from a radius of convergence to an interval of convergence. That means my interval of convergence would be 3, 7. And it's either a bracket or a parentheses. Well, Mr. T, how do I figure it out if it's a bracket or a parentheses? Well, I will show you how. All right? The way you figure out if it's a bracket or a parentheses, please let me go up. Oh, sweetie, sweet. The way we figure it out is kind of nice because we've already done this stuff, okay? I'm going to kind of break it off there. The way I figure out if it is, if we include the endpoint or we disinclude that endpoint, is I just use this value 3 and I plug it into the original problem for x. So we have a series n equals 1 to infinity. Oh, snap. This alternator may actually come into play. Okay, I'm going to put a 3 in there, so I get 3 minus 5 to the n all over, what do we get here? N to the 2n. All right, so I probably got to simplify a little bit here. Ooh, I'm going to come down here. Okay, equals, let's go this guy. How could I simplify? Well, that ends up being negative 2 to the n. And negative 2 to the n would be negative 1 to the n times 2 to the n. We all buy that, right? That's kind of by our Algebra 2 rules of exponents, right, class? And that's all over n 2 to the n. Now, swing, swing! Okay, the next thing I want to do is I have these negative 1s up there, right? And they're the same base. So if they're the same base, remember, I can combine them. And that's going to give me negative n. And remember, whenever we combine, we add exponents. So that's going to give me a 2 to the n plus 1 all over n. Okay, okay. And then if I really want to inspect further, is this indeed an alternator? Because then I would have to do the alternating series test. Okay, is that an alternator? Well, 2n plus 1. If I put in a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, and a 10, what do I get? I always get a negative answer. So believe it or not, negative 1, 2n plus 1 is just negative. So I could bring that negative on the outside, equals 1 to infinity, 1 over n. Oh, snap, that's a p-series. It's a harmonic p-series. And harmonic p-series always diverge. So guess what? That means this has to be a parentheses. Because since it diverges when your x equals 3, we cannot include that. But from 3 to 7, I'm good to go. Now let's check 7. And you know what? We'll do it in blue so we don't get confused. How do I check 7? Well, guess what? You're going to just put that guy. We know everything in between is good to go. We just have to check the endpoints. So in this time, instead of x minus 5 to the n, it's going to be 7 minus 5 to the n, all over n to the 2n. Now, we all know 7 minus 5 to the n is just 2n, so swing, swing. And then we get here, 1 to infinity, negative 1 to the n plus 1 over n. That is definitely an alternator. So that means alternating series test. How do we do that, guy? Well, it's 2 steps. Remember, we throw out the alternator. Okay, we throw out that alternator. And if we throw out that alternator, we got step 1, 1 over n. Whoops. Does that limit as n approaches infinity of 1 over n, does that equal 0? It does, so we're good to go, sweet. And then we got to check, sorry, class, 2. 2 is 1 over n. Is that a decreasing sequence? And we said is a decreasing sequence. And since it is, we know that this converges by the AST. AP loves these questions. Loves them, loves them, loves them. So make sure you get good at it. So then we come back here into the problem. Oh, yeah, my pen probably doesn't work. But we know that 7 is good. 7 is good, but we are going to use the bracket. So my final answer for this would be this problem has a radius convergence of 2. And the interval of convergence would be from 3 to 7. Do not include the 3, but definitely include the 7. All right, let's keep going. I got to get this done. I got to try a half hour. I'm sorry if I go a little bit over. All right, class B is on your own. Let's do, and make sure we go over B in class. Pretty, please. And let's do C together, because C could be a doozy. All right, so there we go. There's your problem. Let's go to my blank screen here. Hopefully my pen is still good to go. Let's go ahead and do another one. Let's check out another series. And is it a power series? This one's n equals 0 to infinity. This is -1 to the n. Looks like we got an alternator there. Oh, but that's x to the 2n plus 1 all over 2n plus 1 factorial. Well, this is centered at 0. This is Maclaurin. All right, even though it's Maclaurin, I still want to check what the radius of convergence is and the interval of convergence. So what values of x am I good to go? All right, let's check this bad boy out. So I'm not going to go little AST stuff right off the bat, right? Why? Because it's a power series. Why is it power series? Because it has an x. Because it's got an x in it, all right? So anytime we have problems like this, we start with the ratio test. And the ratio test says, RT, maybe we should do a good job of saying what we are doing. The limit as n approaches infinity, absolute value. What could I do with that alternator? See ya, see ya, see ya. Because the absolute value of a negative is always a positive. Okay? All right, so then we got a little bit of x. Ooh, and then I'm going to put an n plus 1 in there. Ooh, so let's be careful. That'll be 2n plus 1 plus 1 all over 2 to the n plus 1 plus 1 factorial. Hopefully I didn't lose anybody there, but that seems legit to me. Divided by reciprocal, right? Or, sorry, multiply by the reciprocal of the original. Okay, once again, don't need that alternator. We get rid of that guy. All right, there's probably some simplification stuff I need to do. Let's check it out. That would be x to the 2n plus tree all over 2n plus tree factorial. Oh, snap, there's even some more simplifying I need to do, because right now I can't get a little spling, right? Boom, not yet. I can kind of see it, though. But, hey, you know what? Mr. Tanaka, I just used third person. I apologize. Don't ever do that again, okay? Your AP grader loves to see all of your work, okay? So that'd be 2n plus 2. And then it would be 2n plus 1 factorial. Okay, and then we might get some splings, right? Over x to the 2n times x. What do we get here? Spling. And so that gives me, let's go up here a little bit. Oh, all right, let's go up there, and that gives me the limit as n approaches infinity of x cubed over x, so that'd be just x squared. I'm going to simplify that, right? Those guys kind of can simplify there. And then on the bottom, what do we get? We get a 2n plus tree and a 2n plus a 2. Okay. Oh, x squared. Well, that's just a constant, right? Since that's just a constant, we can plug infinity, x, a constant over infinity. Well, that's just going to be equal to 0, and 0 is less than 1. Now, do we remember what that tells us? If 0 is less than 1, then we say, ooh, this one was not too bad. Let's write our conclusions here. That means this, ooh, the radius of convergence is infinity. That means the interval of convergence would be -infinity to infinity. So, man, I had all my notes here. This looked like a lot of work. That actually wasn't too bad at all, was it, class? All right, let's go on to the last one then. Okay, we got one more we want to do with you. Let's get back here and use this full screen. Remember, you did B on your own. All right, now we got D. D is the series n equals 0 to infinity. All right, let's see what this one looks like. That's n factorial times x minus 3 to the n. Ooh, this one looks a little bit different. I don't even have a ratio. But this is definitely a power series. Why? Ching, ching, because there's an x in it. X always means it's a power series. Whenever it's a power series, you got to find the radius of convergence and the interval of convergence, right? And this is centered at 3, right? So our C would be equal to 3. Can I venture out from that a little bit? Can I go 1 to the left, 1 to the right? Well, we are about to find out. How do we find out? The ratio test. All right, so here we go, RT. Let's do that ratio test. We got the limit as n approaches infinity. All right, so we got the n plus first term, which would be n plus 1 factorial, x minus 3 to the n plus 1. And we are going to divide that by the a sub n. Ooh, I don't even have to do a little multiply by the reciprocal here, right, class? So I got this guy down here. All right, remember, if that's less than 1, that's when it would converge. That's what the ratio test tells me. But I've got to simplify a little bit. On the top, I got n plus 1 times n factorial. And then I could write that as x minus 3 to the n times x minus 3 to the first, all over n factorial times x minus 3 to the n, spling, 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 spling. And we get, check it out, let's keep it rolling, equals the limit, right? My ratio test is not done until I take the limit. All right, absolute value. Ooh, I get n plus 1. And I get x minus 3. And then there's what? Nothing in the bottom. You plug an infinity in there. X minus 3 is just some constant. Infinity times a constant is equal to infinity. That is greater than 1. That means it diverges. What the heck does it mean it diverges? This means it. Ooh, let's write my conclusion. What is the radius of convergence? The radius of convergence. The radius of convergence is 0. It's 0. Why? Because it diverges for everything. But remember, it always converges at your center. So we would say that, well, how do I write this? I mean, you write just tree, right, in a little bracket. I mean, that's the only guy that's good to go. That is it. So this means it diverges for all values of x except 3. That's it. Radius convergence is 0. How about it? So we did every particular case. We're going to have to do a lot of practice here, all right? But I gave you some homework to do. Make sure you get that done. Make sure you get B done. Let's make sure we go over it in class. Aloha. I'm praying it's under 30. I don't get a clock anymore. Home's not helping me out. Let's go.